We are starting with process models. Process is an abstraction of a running program. This concept turns a single CPU into multiple virtual CPUs. In multi-programming system, the CPU switches from process to process quickly, running each for tens or hundreds of milliseconds. At any one instant, the CPU is running only one process. In the course of 1 second, it may work on several of them given the illusion of parallelism. This is a pseudo-parallelism. All software, including operating system, is organized into a number of sequential processes. We call it processes for short. A process is an instance of an executing program, including the current values of the program counter, registers, and variables. In fact, we have one program counter in the CPU. That counter, for example, starts with process A. When that code finishes, it passes to the process B and then passes to the process C and D, etc. This is multi-programming of 4 programs. However, conceptual model of 4 independent sequential processes can be thought as if they are executing in parallel, although they are executed sequentially because we have a single processor here which has a single program counter. If we consider real execution in time, for example, first process A executes for some time, for example, while it is doing I/O operation, the processor may continue with the process B, and when it terminates or if there is an I/O operation, it passes to the process C and then to process D. Then, if the process A is ready, meanwhile, it goes back to the rest of the process A, then continues with B, C, and D, etc. If we consider a particular time, at that time, there is only one process is executed. For example, at this time, B is executing, at this time, C is executing. The difference between a process and a program is that the program is a group of instructions, whereas the process is the activity of some kind. A process has a program, input, output, and a state. Normally, a process should not be programmed with built-in assumptions about timing. When a process has critical real-time requirements, that is, particular events must occur within a specified number of milliseconds, special measures must be taken to ensure that they do occur. Creating new processes is particularly useful when the work to be done can be formulated in terms of several related but otherwise independent interacting processes. For example, fetch and process tasks. In general purpose systems, some way exists to create and terminate processes as needed during operation. 4 principal events that cause processes to be created are as follows. 1. System initialization. Processes can run either foreground, interacting with the user, or background. Background processes are called daemons, handle activities such as email, printing, etc. Windows Task Manager shows them. 2. Execution of a process creation system call by a running process. 3. A user request. 4. Initialization of a batch job. After fork, 2 processes, parent and the child, have their own distinct address spaces, the same memory image, the same environment strings, the same open files. If either process changes a word in its address space, the change is not visible to the other processes. In Unix, the child's initial address space is a copy of the parent's. No writable memory is shared. Typical conditions which terminate a process are 1. Normal exist. This is voluntarily. 2. Error exit. Voluntarily. 3. Fatal error. Involuntary. 4. Killed by another process. Involuntary. In Unix, a process and all of its children and further descendants form a process group. Init system call is present in the boot image. It starts running, reads a file telling how many terminals there are, forks off a new process per terminal. Each new process waits for someone to log in. If a login is successful, executes a shell to accept commands. In contrast, Windows has no concept of a process hierarchy. A process may be in one of the following states. 1. Running state. In this state, the process is actually using the CPU at that instant. 2. Ready state. This state is corresponding to the case the process can be executed but temporarily stopped to let another process to run. 3. Block state. In this state, the process unable to run until some external event happens. For example, I/O operation, or it may be forced to be blocked for some other reason. A process can be in running, blocked, or ready state. When a process is executing, when it is in the run state, if the process needs an I/O operation, then its execution is blocked and it passes to the blocked state for the I/O. Or while a process is executing, the scheduler picks another process, then the executing process passes to the ready state, and the one chosen for the execution passes to the running state. Always the processes from the ready state are chosen for the execution. When scheduler chooses our process, it passes from the ready state to the running state. When a process starts, it enters directly to the ready state. When a process completes its I/O operation, it passes to the ready state. The lowest layer of a process-structured operating system handles interrupts and scheduling. Above that layer, there are sequential processes. Here we have n processes numbered as 0, 1 up to n-1, and this is the scheduler to organize the execution of the processes. When a process starts execution, a process control block is assigned to it. Some of the fields of a typical process table entry is shown here. It is also called process control block. In the process control block, we have an area for the process management, another area for the memory management, and also for file management. In the process management area, we have fields to store the content of the registers, program counter, program status word, stack pointer, process state, priority, scheduling parameters, process ID, parent process, process group, signals, time when process started, CPU time used, children's CPU time, time of the next alarm. In the memory management area, we have pointer to next segment information, pointer to data segment information, pointer to stack segment information if segmentation is used for the memory management. If we are going to use some another memory management technique, then this content may be different. In the file management part of the process control block, information about root directory, working directory, file descriptions, user ID and group ID is stored. Switching between processes occurs as explained below. While process A is executing, suppose that it needs an I/O operation, for example, then it goes to the block state. Before that, the value of the program counter while process A is executing is stored to the related area of the process control block of process A. And also, the content of the registers at that moment are stored into the registers area of the process control block of process A. Assume that the next process to be executed is process B. Then it is needed to load the content of the program counter for process B. And also from the control block of process B, the content of the registers when that process is removed from the memory is loaded back to the registers considering the related area of the process control block. All these operations are called context switching. And then process B continues its execution. Sometimes later it may be needed to remove the process B from the processor, and instead of that, process A to continue its execution. Again, similar operations are needed. Save the content of the program counter for process B, save the content of the registers for process B into the process control block, and load program counter value for A and load register value for A. These are loaded from the process control block of process A. This is again context switching from process B to process A. And after that, process A continues its execution. Here it's given the skeleton of what the lowest level of the operating system does when an interrupt occurs. 1. Hardware stacks, program counter, etc. 2. Hardware loads new program counter from interrupt vector. 3. Assembly language procedure saves registers. 4. Assembly language procedure sets up new stack. 5. C interrupt service runs, typically reads and buffers input. 6. Scheduler decides which process is to run next. 7. C procedure returns to the assembly code. 8. Assembly language procedure starts up new current process. A process may be interrupted many times during its execution, and after each interrupt, the interrupted process returns to precisely the same state it was in before the interrupt occurred. Execution of a process means CPU operations on the process, such as changing its variables, performing arithmetic operations, etc. It may be also named as processor CPU burst. I/O work means Interaction of the process with the I/O devices such as reading something or writing to somewhere. It may also be named as I/O burst. We classify programs as processor CPU bound program. This is a program having long processor bursts, execution instance, but shorter I/O bursts. The other one is I/O bound program. This is a program having short CPU bursts but longer I/O bursts. Assume we have two processes A and B. Both execute for 1 second and do some I/O work for another 1 second. This pattern is repeated 3 times for process A and 2 times for process B. If you consider task A, it has execution, I/O, execution, I/O, execution, I/O. This is saying that it is the first execution of process A, the first I/O for process A, then second execution for process A, second I/O for process A, etc. For process B, we have execution, I/O, execution, and I/O. These are for process B and the first execution, first I/O, etc. If we have no multi-programming, the processes are executed sequentially as below. Here process A starts execution, execution A1, I/O A1, execution A2, I/O A2, execution A3, I/O A3, and all the operations for the process A is completed. Then A terminates and it leaves the system. After that, B starts its execution, execution B1, I/O B1, execution B2, I/O B2. And then process B terminates, it leaves the system. Time is going from left to right. So the processor executes these two processes in total time of 10 seconds. This is time 0, and when we come to this point, it is time 10, so the total time is 10 seconds. However, the processor is idle during I/O operations. That is, processor is idle for 5 seconds and it is used for 5 seconds. If you consider the processor utilization, it is calculated. The time processor busy is divided by the total time multiplied by 100. So the processor utilization is 50%. Now let's consider multi-programming. Here the timing is given for CPU and for I/O. This is called Gantt chart. Here in this chart, compared to the execution times, because it's a small, context switch time is ignored. First, A enters to the ready queue and then immediately chosen for execution because there is no other process in the system. This is the first execution of process A, then it requires I/O operation. Meanwhile, the I/O device was idle. Because A is doing its first I/O operation, process B can start its execution. When B enters to the system, it enters the ready queue and it waits until the first execution of the process A completes. This is the process executing and this is waiting in the ready queue. Here, because process A leaves the CPU for I/O, process B can start its execution. This is the first execution of process B. And by chance, in this example, when the execution of process B finishes and it requires I/O operation. Also, the I/O operation for the process A finishes. Then A is loaded into the CPU and B starts its I/O operation. Here we assume that they are using the same I/O device in order to show it easily. Otherwise, we should need a chart for each different I/O device. And let's continue. Here, the second execution of A terminates and first I/O of B terminates. B starts its second execution when A finishes its second execution. Meanwhile, B finishes its first I/O operation. B starts its second execution and A starts its second I/O operation. Then again there is a switch. A starts third execution while B starts its second I/O operation. At this point, all the operations for B is completed and B terminates. For A, this is the third execution. When it finishes, it goes to the I/O device and here it terminates. Notice that CPU is idle here at the end, while I/O is idle in the beginning for this example. In the multi-programming case, while process A is performing I/O work, that is, not using the processor, CPU utilizes its time to execute process B instead of being idle. If we consider the total time, it is 6 seconds. So the processor utilization is 5 divided by 6. This is the time processor is busy and it is divided by the total time multiplied by 100. Processor utilization is 83%. Notice that context switch time is ignored. If it was considered, then process utilization would be smaller than this value. Here it is explained the CPU utilization in terms of degree of multiprogramming. Assume that a process spends a fraction p of its time waiting for I/O to complete. With n independent processes in memory at once, probability that all n processes are waiting for I/O, meaning CPU is idle, is p to the power n. In this figure, CPU utilization as a function of the number of processes in memory is given. This axis is showing the degree of multiprogramming, while this is corresponding to CPU utilization in percent. The curve is drawn for different p values. If it is 0.2, then this is the corresponding curve. It is also given for p equal to 0.5 and 0.8. Notice that whatever the value of p, as the multiprogramming degree n increases, the CPU utilization increases also, but after some point on, the CPU utilization saturates.